Okay, as promised, we are going to get into some math dealing with thermodynamics. So we're going to talk about both calorimetry and Hess's law. So let's start with calorimetry. Now, I know we have talked about this equation before, and the parts of the equation have not changed, right? Q is equal to heat, M is mass, C is specific heat, and T is temperature. But I don't think we've ever really talked about calorimetry and exactly what calorimetry is and what a calorimeter is, something that you do calorimetry in. So here are two pictures of calorimeters and we're going to talk about exactly what is going on here. All right, and so what we're going to look at, I don't know why this is misbehaving so badly today. So what we're going to look at today is, or in this slide, is exactly how this calorimeter is working, right? So essentially what happens is you have a reaction chamber, right, where that's in both of them that tends to be sealed. You have something that ignites your sample, right? So we're usually burning the sample, right? So it's going to ignite it. You have water surrounding it. And you have something to take the temperature, a thermometer, of the water, right? So you look at the change in temperature of the water as your reaction happens, and that way you measure the amount of energy that is coming out of your reaction. And based on this lovely equation here, you can figure out the amount of energy released by your reaction based on the change in temperature of the water. And so we will be doing this in a lab. You will get to burn some things and measure the temperature of the water, or the change in temperature of the water, and be able to figure out how much energy is coming out of those things that are being burned. So that's calorimetry and a calorimeter, the basics of it anyway, right? You have a sealed container, you have something that ignites, you have water that you are measuring the temperature of to figure out the change in energy. Okay, on to Hess's law. So Hess's law, if a reaction is carried out in a series of steps, delta H for the overall reaction equals the sum of the enthalpy changes for the individual steps. Great. So what does that mean? It means that we can take multiple reactions that we know the change in enthalpy for and combine them to calculate the change in enthalpy for a reaction that we do not currently have thermodynamic data on. Great. I can't wait to do it. Fantastic. Let's do some. So a question might be, calculate the change in enthalpy for the following reaction. All right, and we have this reaction up here that we are interested in learning something about, right? Right there. Great. Now, what we are given the following three chemical equations, 1, 2, 3, and we are given some enthalpy information about them. So these are the enthalpy changes for these reactions. Now, what we want to do is somehow combine these three equations to make this one. So we're going to do some things to these three equations down here, equations 1, 2, and 3, so that we can get to the one we want up here. Now, just like mathematical equations, we can do pretty much anything we want to these equations as long as we are consistent and do things both to the equation itself and to the enthalpy value that results from the equation. So if you look here, right, we want C2H2 as a product, yet here it is as a reactant. So what we can do is we can flip that first reaction, right? And so we flip the first reaction. So now we have made our reactants our products and our products our reactants. But if you notice, all right, what we have done is we have changed the sign of the enthalpy, because as we flip that, right, and if I go back, all right, it's negative here. And then as we flip it, it becomes positive, right? So as we flip the equation, we have to flip the sign of the enthalpy for the equation as well. Great. So now we have this stuff. We can start even looking. We can say, oh, we can cancel out our waters. We can cancel out 1/2 of our O2, leaving us with 4/2, or, right, 4/2 is 2, right, 2O2. And yeah, that's where we can stop for the moment, because if we look, right, we don't want CO2 in our final equation, but we've got 2 CO2 right here, but only 1 CO2 right here. So what we can do is we can multiply that second equation through by 2, and we get something like this, right? Everything gets multiplied by 2, including the enthalpy. Right, so if I go back, we look, negative 393.5. When we multiply everything through by 2, we get negative 787. All right, and so now we look, we've got 2 more O2s. We cancel those out. We cancel out our 2 CO2s. We are left with 2 carbons, 1 hydrogen, and 1 C2H2, which is exactly what we want for our final equation. The only thing left to do now is to add up all of our enthalpies to get an answer of 226.8 kilojoules. And so that is the enthalpy change for this reaction. The next thing we can talk about is enthalpy of formation. So we define this as the enthalpy change associated with the formation of a compound from its component elements. So, and using these enthalpies of formation, we can calculate the enthalpy of a reaction, right? Kind of like we did with Hess's law, using the following formula, in that the enthalpy of reaction is the sum, right? If you are not familiar from math with sigma, that means sum. The sum of the enthalpies of formation of the products minus the sum of the enthalpy of formation of the reactants makes the enthalpy of reaction. So, of course, we're going to do some calculations with this. So, a question might be, calculate the standard enthalpy change for the combustion of 1 mole of benzene, right, that's C6H6, as a liquid forming carbon dioxide gas and liquid water, right? So this is going to be important that we know the states of our reactants and our products, because the enthalpy of formation is determined by the state of your compound. So we have a balanced chemical equation. You might notice, you probably noticed in the last one, and you will, I'm sure, notice here, that we have fractional balancing numbers. Now, I know I have probably told you that that is illegal. I am retracting my former statement and saying that now that you have graduated to the level of a chemistry student who is involved in thermodynamics, you can use some fractional balancing numbers. And why do we have to use fractional balancing numbers here? Because we have said calculate the standard enthalpy change for the combustion of 1 mole of benzene. And if we are forced to have a 1 as a balancing number for benzene, that means that we must have a fractional balancing number here for O2. And so we do. So now, calculating the enthalpy change for this reaction, we're going to look at the enthalpy of formation for each of these. So we first write out our equation that's going to look like this, where we have the enthalpy of reaction is equal to 6 moles times the heat of formation of CO2, right? Because remember, this is products minus reactants, right? Products minus reactants, plus 3 moles times the heat of formation of liquid water, minus 1 mole, the heat of formation of benzene, plus 5/2 times the heat of formation of oxygen. All right, so that's what our reaction is going to look like. From there, we're going to look in a chart to find these heats of formation and put those numbers in. Now, I want you to notice one very specific thing over here, that the heat of formation of oxygen is 0. And that is going to be true for the heat of formation for any element, right? So if something is an element, whether or not it is 2, like in the case of O2 or H2 or F2 or Cl2 or N2 or Br2 or I2, right? Any of those things that are diatomic, the heat of formation for an element is always 0 because that is its standard elemental state, so we do not count that as having a heat of formation. So elements will always have a heat of formation of 0. Everything else will have a heat of formation. You find those in charts. I have put them here. And now, at this point, it really becomes just multiplication, addition, and subtraction. And so when we do all of that multiplication, addition, and subtraction, we can break it down to this, and then finally a heat of reaction of negative 3,267 kilojoules per mole. So, and if you think back to the last video, we can say that this particular reaction then is exothermic because we have a negative value for our enthalpy of reaction, meaning that energy is being released. Okay, the last thing that we're going to talk about here and do some math with is bond enthalpies. And what bond enthalpies are, this is the energy that is required to break or make bonds. And so bonds require energy to break them and release energy when they are formed. So the change in the number and type of bonds present before and after a chemical reaction can be used to calculate the enthalpy of reaction using the following formula. That again, enthalpy of reaction equals the sum of the enthalpies of the bonds broken minus the sum of the enthalpy of the bonds formed, right? Because remember, we are needing to use energy to break them, and we are releasing energy to make them. So, what you've all been waiting for, example time. The question, estimate the enthalpy change of reaction for the combustion of ethane. So the first thing we're going to do is write our balanced chemical formula, which is going to look something like this. And then we are going to figure out how many bonds are in there and write our equation. So if we look, and this is where it will be helpful to be able to draw out molecules. Right? So if we look at our C2H6, right, it would look something like this. All those great Lewis dot skills coming back. All right, so that's what our hydrocarbon is going to look like. O2 is going to look like that. CO2 looks like this. And H2O, of course, looks like this. So we count up the number of bonds. We have 12 carbon-hydrogen bonds, right? Because we have 2 moles of our C2H6. So if we have 6 carbon-hydrogen bonds in 1 mole, then we have 12 carbon-hydrogen bonds in 2 moles. And we also, from those 2 moles, have 2 carbon-carbon bonds, right? Plus, because we have 7 moles of O2, we have 7 oxygen-oxygen double bonds. And on the product side, right, what we're forming, we are forming 8 carbon-oxygen double bonds, right? Because we have 4 CO2s and there's 2 double bonds in each of them. And we are forming 12 oxygen-hydrogen bonds because we've got 6 moles of water, 2 bonds each, right? So we've accounted for all of the bonds in this reaction. So then we're going to look up on a chart and find our bond enthalpies, and we put those values in. And so now we have put the values in for all of our bond enthalpies. And again, now that we have everything in here, this just becomes multiplication and addition. So we can simplify this, right? So there are our bond enthalpies broken and formed. And then we just do that final math. We get our delta H, or our enthalpy of reaction, and we see that we have released, right, because it's negative, so released 2,831 kilojoules, which means, again, this is an exothermic reaction. Okay, and that is it for that video. We will have another video on thermodynamics where we talk about entropy and Gibbs free energy, and that will do it for this unit.